day 2 warm-up for honors geometry. Just going over it since I'm not there in person to go over it with you, so I went to kind of look at this. It says you were supposed to draw a diagonal in the square, so it doesn't have to be perfectly straight, we're just going to draw a line. Determine the angle and measures in the triangles that were formed. Well, we know in a square this is 90 degree, and the diagonals bisect the angles in a square. So this is 45 and 45. Okay, so these little degree symbols, we would have a 90 degree symbol. Or here, let's start with 45. We'll have a 45 degree, 45 degree, and 90 degrees. Alright, so using Pythagorean theorem, find the missing length. So they're wanting you to draw in the diagonal for this. Reminder, just a reminder, Pythagorean theorem, a squared plus b squared equals c squared. Remember, the hypotenuse is always located opposite the 90 degree corner, which we've already done Pythagorean theorem on day 1, so it should not be a difficult concept. Okay, so I'm going to make that x. And on day 1 we learned when you take the square root at the end, we want to simplify this. So the square root of 18, we want to simplify by breaking down that radical, not getting a decimal. That would be 9 times 2, because 9 is a perfect square. The square root of 9 is 3, square root of 2. Okay, so given this is a square, because all the sides are the same, finding the diagonal. Let's try it again now, only this time the sides are going to be 5. So same idea, finding the hypotenuse in this square. Going to simplify that by breaking down that to square root of 25 times 2. Remember, your perfect square always goes on the left, so that answer is 5 square root of 2. I want you to look back now. If this diagonal was 3 square root of 2 and this diagonal is 5 square root of 2, do you think there's a pattern in finding the diagonal of the square? Or, more specifically, because this is a 45 degree triangle with 90. Same thing here. These are squares, these are 45 degree angles and a 90. So at the top we wrote that drawing the diagonal cuts us in half, so these are called special right triangles, because if the two legs, the two sides are the same, then if this is 45 to 45 degrees on both angles, you'll notice the diagonal always comes out to the same thing. So today we're going to be talking about special right triangles. So if you have a, let's write that again, 45 degree, 90 right triangle, meaning both, it's isosceles, two of the legs are the same in the isosceles. We're going to choose n for number. Whatever the number on the side is, they have to be the same because it's isosceles. Then if these two are the same, the hypotenuse is always going to be that number times the square root of 2. This is a formula that we get to memorize this chapter, that if this is 5, this is 5, then we know that the diagonal is going to be 5 square root of 2. Same thing here. This is 3, then the diagonal always comes out to 3 square root of 2. And you can do that for any amount of numbers you want on the side. If this was 9 and 9, this would be 9 square root of 2. It follows the same pattern all the time. That's why it's called a special right triangle. Okay, let's look at the next one. Draw the perpendicular bisector of one of this equilateral triangle. So I'm going to draw perpendicular the best I can, bisector. Okay? So if you do that, we know in an equilateral triangle all the angles are 60 degrees. But that perpendicular bisector is going to make this 30 degrees. So we call this one a 30 60, 90 special right triangle. Okay? So, in this one, use Pythagorean theorem to find the missing side. Let's draw in that perpendicular bisector. So we want to find this height right here. Okay, because if this is split, if it's bisected, we know this part is 2. This 4 is your hypotenuse. Okay, so if you were going to set this up, we would do like, you can either do x squared plus 2 squared, or 2 squared plus x squared equals 4 squared. 4 would be like our diagonal in this case, across from the right angles. And subtract 4 to the other side after squaring those. Now I have to take the square root of 12. So let's see what that comes out to. Square root of 12 can be divided by 4. Remember your perfect square list. So that would be 4 times the square root of 3. So the answer is 2 square root of 3. Okay, that's how that's simplified. Let's try the next one. This time we have 10s on all sides of our equilateral triangle. So if we split that down the middle, that creates this side to be 5, and we don't know that side. So we'll square those numbers, subtract 25 to the other side. I'm going to square root 75 to get it by itself. 75 can be broken down to 25 times 3. Remember, you still have to square root the 25, so that answer would be 5 square root of 3. So look at our answers. When we did Pythagorean theorem with a 30, 60, 90 triangle, this is the 30 degree, this is the 60 degree. This is the 30 degree, this is the 60 degree. So we want to come up with kind of like a special rule like we did for the other ones. So if you look at that, the smallest angle across from the 30 degrees is just, we're just going to call this n. Okay? So if this side is 5, this side was always n times square root of 3. Whatever this number was times the square root of 3. That's what that number is. So we have to figure out, how can I go from 5 to 10? What could I write as a rule for that? Well, 5 times 2 is 10. Let's see if that works up here. 2 times 2 is 4. So this is just 2 times n. Whatever number this is, you times it by 2 to get the hypotenuse. So these represent the angles. These represent the sides across from the angle. So this would be like your hypotenuse side. This would be your short leg. This is considered like your long leg. When you have a 30-degree angle, opposite the 30-degree angle is your shortest side. Opposite the 60-degree angle is your longest leg. And then this one's called the hypotenuse. So when you're trying to identify, this is the rules that you would use on those special right triangles. Those always come out to the same pattern in the numbers. That's why it makes it special.